Okay, so now we will solve this problem. This is a simple ideal Brayton cycle. So this is the TS diagram. In this TS diagram, you can see all the phases from 1, 2, 3, 4, and all the corresponding values are given. You can see here the pressure ratio is given 8, the RP pressure ratio. This is actually the isentropic process. This is the isentropic process. You can see x-axis isentropic means no entropy change here. The pressure is constant for this process 2 to 3 and also for this port 1. So you see we have the work input here, the work output here. This is for compressor, this is for the turbine. So we have the heat in here and the heat rejection here. So that's actually the overall the TS diagram of this Brayton cycle, and we discussed it earlier. So now we'll try to solve in this question. You will see the temperature for the compressor inlet. So this is the compressor inlet, this is the compressor outlet. For compressor inlet, the temperature is given, you can see 300 Kelvin, and this is actually for the turbine. For the turbine, you can see inlet, the temperature is given 1300 Kelvin, so 1300 Kelvin here. What we need to calculate is using the air standard assumptions. We already discussed the air standard assumptions at the very beginning of the lecture. So we need to calculate the gas temperature at the exit of the compressor and the turbine. So we need to calculate the gas temperature. So we know the inlet temperature for compressor and the inlet temperature for the turbine. Now we need to calculate the exit temperature of the compressor and the exit temperature for turbine. So that's the first part. Then the backwork ratio and the thermal efficiency. So we'll gradually solve this question. So the first part is the assumptions. We will consider the Brayton cycle. It is the steady flow device, and because all the compressor and the turbines we are using, this is a steady flow device. So let's say it is a steady state condition. Okay, so that's the first assumptions here, and the second assumption is it says the air standard assumptions. I'm not telling the air standard assumptions again here. You can see from the lecture slide, and we already discussed it. So the air standard assumptions applicable here. Okay, so that's the second assumption. Third assumption, we can say the kinetic energy change and the potential energy change, it is negligible. Okay, so we can say it's very close to zero. So that's all of our assumptions. So first part of this question is, it is asking about, we need to calculate the exit temperature of the compressor and the exit temperature of the turbine. So here you see this is actually the compressor and this is the turbine. So now we will start with the analysis. So when we will start with the analysis, we actually need the exit temperature. So at first we will calculate it for pump. For pump, we know the inlet temperature 300. Okay, and it is actually the process 1-2 process. So process 1 to 2, we can say the process 1 to 2. And what it is actually, you can see it is a vertical line. So we can say it is isentropic process, right? Yeah, so we can say this is isentropic process. An isentropic process means no change of the entropy. Here, actually, in this case, we will consider this problem. You can see this is a gas turbine power plant. So this is an ideal Brayton cycle. So we will consider this is actually the isentropic compression for ideal gas for process 1 to 2. So for process 1, the temperature, we will say for process 1 the temperature is T1. For process 2 temperature is T2. So T1 is given 300 Kelvin. Okay. So for this 300 Kelvin, if you see we know the properties of the ideal gas. For 300 Kelvin, so this is for 300 Kelvin. We can see for 300 Kelvin, this is actually this 300.19, it is the enthalpy, and this PR, this is actually the relative pressure. The relative pressure is the dimensionless quantity. So we got these two values. So what we will do, we will write it here. I will answer why we are taking this. So the enthalpy has one, it is equal 300.19, and you know the unit is kilojoule per kg. Okay, and we got one more PR, which is the relative pressure. One means for the inlet of this compressor. This value is 1.386. You can ask me why you got this. We understand that maybe you need the enthalpy to calculate the work input or the work output, but why you need the relative pressure? Yeah, that's the question, because we know here in this question we know the pressure ratio. It is given. We don't know the specific pressure P1 P2, but we know P2 over P1 it is 8. But from this value, if you look here, if you actually want to get the temperature for the exit from this ideal gas of the air, if you somehow know the the enthalpy or the relative pressure, then you can easily get the temperature. So what we did here is, we know the inlet temperature for this compressor is 300 Kelvin, and for 300 Kelvin we got these two value. So suppose in this question the enthalpy is given 300.19. So if we do this modification, we say the enthalpy of the compressor inlet is 300.19 kilojoule per kg. Then if I say, okay, calculate the inlet temperature of the compressor. So then you need to go to the ideal gas properties. You will see where is this value. It is 300.9. So if this value is correspond to this temperature 300. So I believe you understand. So if you know any of these two values, like the enthalpy or the pressure ratio, the relative pressure, then you can get the corresponding temperature. Here what we did, we know all of these values for T1. Now we need to calculate T2, and actually we don't know anything for T2. If we can calculate PR2, that means the relative pressure for the exit of the compressor, then we will be able to get T2. What I said if we want to get T2, okay, that's our target. So if we know the PR2, that means the relative pressure at this exit of the compressor, then if we know, let's say for example, this is actually the relative pressure at the exit, then the exit temperature will be 330. I believe you understand. So the question is then how we will calculate that. From the ideal gas relations, we know the pressure P2 P1, it is actually equal to PR2 PR1. That means the pressure ratio, it will be equal to the relative pressure ratio. And in this question, this pressure ratio is given 8. So what we can say here, we can say we actually need PR2. So we can write PR2, it is equal P2 P1 into PR1. So now you see this P2 and PR, it is given 8. So we can write it is 8, and PR1, here we got 1.386. So you can say 1.386. So if we solve this, then we will get it is 11.09. You may ask, what is the unit? It has no unit. It's a dimensionless quantity. So that means we got PR2, it is equal 11.09. Okay. So for this 11.09, we will see where it is. Look, 11.09. So this is the value. 11.09 means 11.10. So we can say it is 11.10 and the corresponding temperature is 540. So we can say T2 it is equal 540 Kelvin. So this is the first findings according to the question. So we got the temperature at the exit. I believe you understand, guys. So also we can see the enthalpy is 554.35, 544.35. So we can write down for this value H2 it is also 554.35 kilojoule per kg. So this is another value. We need it when we will calculate the work input and the work output or later on. So now we have done this. And the other part is, we know the turbine inlet temperature, isn't it? We need to calculate the turbine outlet temperature here. Turbine inlet temperature is 1300. So we can say this is part B or part 2. So we know the temperature T3, it is equal 1300 Kelvin. So for this 1300 Kelvin, you see when it is 1300 Kelvin, what it is. Yep. So I just, it just goes down. So for 1300 Kelvin, I'm writing, you will get this table from the book. So for 1300 Kelvin, we know from this table A. So this is table A17, okay? Table A17 from your textbook. So A has 3, it is equal, 1395.97 kilojoule per kg. Kilojoule per kg. And PR3, it will be 330.9. This is dimensionless constant. So now again, we can use this expression. So we can write it is, let's say, P4 over P3, okay? It is equal PR4 over PR3. What we are looking for? We are looking for PR4. So we can say then PR4, it is equal, P4 P3 into PR3. So what we know, guys, here actually, the gas ratio P2 over P1, it was the RP, if you read the question, it says the pressure ratio for the Brayton cycle pressure ratio is 8. Okay, so the P2 P1 it was 8. So when it is this is actually for the compression process. For the the expansion process, it will be just the reciprocal. We'll discuss it later on. And so that means P4 P3, it will be 1 over 8, and it will be just the opposite. So when it is compression, if it is 8 RP, the pressure ratio, for the expansion, it will be just the reciprocal value anyways. So then it will be 330.9, and we will get PR4, it will be 41.36. So let's see here, 41.36, where it is. Yes, it will go down here, 41.36, the PR4, 41.36. So this value, so it's kind of 780, the temperature, you see, 41.36 or 35, that's the same thing. So we can say or 41.36, then we can do some interpolations. So for the turbine exit, according to the values here, you can see what I said, it is 41.36. This is the PR3 value. So for 41.36, okay, it's not 41, it's 43. So we need to do the interpolations for these two. So we will get the value in between these two. Look here, I thought it's 43.36, it's not, it's 41.36. So we need to interpolation, do some interpolation for these two and these two, and you know how to do this these interpolations. So for the exit temperature T4, it will be actually 770 Kelvin. I believe you can easily solve this. And similarly the Haze 4, this value it will be 789.37 kilojoule per kg. So these interpolations for it was pretty straightforward. We already know you are doing many complex interpolations, so I'm not showing you this one here. So then this is the first part. We have done with the first part. Now the second part of the question is, it says the backwork ratio. The backwork ratio is nothing. It is actually the ratio of the the combined the compressor work and the turbine work. So I will write it down, the formula for you. So for the second part, for the second part of this problem, it says the backwork ratio. So we can say the backwork ratio. The formula we can say the RBW. Backwork, R means the ratio. It is the compressor work and the turbine work ratio. So this is the formula. We are getting the work due to this compressor, and we are getting the output. This is actually the work in. This is actually the work out. So the ratio of this two work, it is the backwork ratio. Okay. So for W compressor in, if you can remember, last time we discussed from the process curve, if we calculate the variation of the enthalpy, then you can say this is actually the equal to the work. So for the compressor we have this isentropic process 1 to 2. So the enthalpy variation we can write it is Haze 2 minus Haze 1. So it will be equal to the work. Similarly, when it is the turbine, for turbine it's going out, so it is turbine work out, and here it is for 3 to 4. So we can say it is so Haze 3, sorry, it is this Haze 3 minus Haze 4. So it will be the work. So that means here you can say it is Haze 2 minus Haze 1 and Haze 3 minus Haze 4. So we already calculated all these values when we calculated the exit temperature. So for Haze 1 we know it was 544.35, and Haze 1 it was 300.19, Haze 3 it was 1395.97, and for Haze 4 it was 789.37. So we will get this ratio is 0.403. So that means you can say 40.3% of the turbine work, 40.3% of the turbine work output is actually used to drive the compressor. So that's actually how we will calculate the backwork ratio. Backwork ratio. Okay, so the last part of this question, it says the thermal efficiency. Thermal efficiency, when we will calculate the thermal efficiency, the formula for the thermal efficiency is the net work over the heat in. You can remember the thermal efficiency formula. We know the eta TH is the thermal, so it is the net work done and the heat in. We used this formula last week. So net work means the work out and the work in, the difference between the work out and work in. And Q in, here Q in means it's the heat is coming this way, so it is actually from process 2 and process 3. So the enthalpy difference between these two processes, we can say H3 minus H2, it is actually the heat in. You understand what I said? So here actually this value, if we calculate this value for and if we calculate this value and the difference, so I should write it down here. So this difference, it is actually 244.16, and this, that means the workout, it is 606.6. So now if we substitute all this value here, for the work output is 606.6, and the work in, it is actually 244.16, and we know H3, the value is 1395.97 minus H2 is 544.35, so it will be 0.426 or 42.6%. So that's how we can calculate the efficiency of this Brayton cycle. So that's the thermal efficiency of this cycle. We can actually use some other formula to calculate the efficiency. So there is another formula. The thermal efficiency is 1 minus the Q heat out and the heat in. So if you want, then you can use this formula as well. So what you need to know, you already know this heat in here. You need to know heat out. So if you actually want to calculate the heat out, how the heat is going out? From here. So the enthalpy difference between these two. So what it is? H4 minus H1. So heat out is H4 minus H1. You already know H4, H1. So then calculate this two value and substitute here. So calculate this two value and substitute in the expression, the heat at T is equal 1 minus heat out over heat in. So then you can use this formula. And now finally you can use if you solve this under air standard assumptions, if you solve it under the cold air standard assumptions, so then if you use this cold air standard assumptions, which means the constant specific heat values for room temperature, then the thermal efficiency for Brayton cycle, the formula is 1 minus 1 over the Rp. This is actually K minus 1 over K. So Rp, this is actually the pressure ratio, and K, it is the specific heat ratio, 1.4 constant. So if you substitute this value here, so this is 8 and K equal 1.4. Actually, if you solve it, then still you will get it is 0.448 or 44.8%. So that's very close. It is very close with this the value we calculated from the net work output. So when we calculated this formula, the net work and the heat in, we got it is 42.6%, and when we use this formula we got 44.8%. So it's very close, so we can easily use any of those, and if you want you can use any formula. You can either use this one, you can either use this one, or you can use this one for thermal efficiency. So that's it.